So what we're going to do today is we're going to start equilibrium, which is a really important topic, and we can't delay it any longer. So I'm trusting that you will work your way through this video, and we'll watch the other videos that are part of this. So let's see how we go with all of this. So this is, as I said, a fundamental concept, and what we're talking about is that chemical reactions can be reversible. So this is something we haven't talked about too much, except in the context of galvanic cells, when we were talking about recharging a secondary cell. So we've had that concept, whereas if you put electricity into a reaction that releases energy, then we can actually reverse it. So there's going to be some reactions that we never consider as reversible, and these were the ones we used for rates. So the irreversible reactions are the ones that you do all your rates calculations with. And it's really important to keep these separate in your mind. The reversible ones, you'll never really talk about rate of reaction when you're talking about a reversible reaction, not to any great extent anyway. Okay, so there's a lot of key knowledge points here. They're very detailed, so we will just go straight into the whole concept of equilibrium. So equilibrium is the topic. So first of all, we need to think about the system. So the idea of a system is our reaction, so our chemicals in a reaction flask, and the outside part too. So we talk about the system and the surroundings. So system and the surroundings. The system can let energy out into the surroundings in any situation, unless your insulation is absolutely perfect. Even then, there's going to be some loss into the insulation. And there's two types of systems that you can have, an open system or a closed system. And I've said here in the notes that an open system is like an open beaker or a flask. Gases can always escape. Whereas a closed system has got a lid on it or it's sealed. So with an open system, then energy and gas, matter can escape, whereas with a closed system, only energy can escape. So let's watch this video, which I think really explains open and closed systems well. Okay, so that gives you a really good example of open and closed systems. So an open system was the wet towel drying on the line with the water escaping into the atmosphere. The closed system was your wet towel in a sports bag where the water goes out into the atmosphere of the bag, and after a while the towel doesn't get any drier. So that's the main thing I wanted you to take from that particular video. Let's move on. So the difference between irreversible and reversible reactions. So an irreversible reaction, the sort, as I said earlier, that we use in our rates experiments, and a combustion reaction has our classic reactants changing into products and no further change occurs. So often there's going to be a gas being produced and that disappears. Well, it doesn't disappear, it leaves the system. And so you just can't go backwards. The picture here at the bottom of the page, the egg being cooked, is also an irreversible reaction. Think about it. You can't uncook a fried egg or a boiled egg or a poached egg for that matter, or scrambled eggs. Let's consider all egg products as being irreversible reactions. So if you're measuring rate, we're dealing with an irreversible reaction, and we won't be talking about equilibrium for that type of reaction. So leave that in a separate little box in your brain for rates. Reversible reactions are an entirely different matter. So the reaction may not reverse spontaneously, or then again it might. The first type of reversible reaction is one that you've known about for a very long time, and that is changes of state, where water as a liquid, when heated, turns into gaseous water. Now, the heat doesn't have to be a great deal of heat. We don't have to be boiling the water. On a warm day, the water on a plant or in a puddle is going to evaporate. And similarly, we can cool any sample of steam and it will condense back to liquid water. So that's a reversible reaction. And when we go from liquid water to gaseous water, we have to add heat. So we are adding heat to go from left to right. And then the opposite of adding heat is going to be removing heat. So if we take away heat from our gaseous water, we're going to turn into liquid water. And so that will be the right to left reaction. So that's a reversible reaction, and we can see that the forward reaction is endothermic and the backward reaction gives out heat, and so that's exothermic. There's a nice little example here on limestone caves. Essentially, I'm not going to go through it in detail, but essentially the formation of stalagmites and stalactites is due to reversible reactions involving carbon dioxide and solutions of carbonates in water. So we move to another example of a reversible chemical reaction, and that's the one involving copper sulfate. Now, copper sulfate itself is actually white. When you see blue copper sulfate, this is a hydrated product. So it's got water tied up in the crystals. Now that dot is not multiplication. We're not in maths. It is actually more like an addition. So it really means that the copper sulfate has associated with it 5 water molecules. So it's a copper with 5 waters, and of course a copper sulfate. If you were working out the molar mass of copper sulfate, with the 5 waters, you would add 5 times the molar mass of H2O. So let's see this reaction in 2 very short clips. Okay, so that was the reverse reaction. This was the copper sulfate with the water turning back into the white copper sulfate. Now, let's see this reaction going the other way. Okay, we don't need to watch the rest of that. So that's the reverse reaction. All right, and the third example is one that you've come across before, electrochemical cells, where rechargeable batteries always involve reversible reactions. So that's your secondary cell. So with your rechargeable battery, the discharging, the forward reaction releases energy, while the recharge requires energy. And you know that because you plug it into the power point. Okay, so how are we going to reverse a reaction? Once you've started making products, then the possibility of the reactants being reformed depends on collision theory, just like our initial rates work. So if the product molecules collide with energy greater than or equal to the activation energy, remember here's our EA there. So if the reverse reaction is going to happen, we've got to get up to that energy, and then the reaction will go in the opposite direction. So as the proportion of products in the reaction mixture increases, the chance of a successful collision will also increase. So it's proportion of products, so percentage of the total, and that increases the chance of a successful collision. So we can look at it like this. As we start out, so where A represents our reactants and B represents the products. So we start out with lots and lots of reactants. And the reactants start to react. And as they start to decrease in concentration, we start to make products. And it goes on with our reactants turning into products until we get to this situation, and this is perfectly easy to monitor in this sort of reaction, where the concentration of the reactants becomes constant. So we have a constant concentration of reactants and also of products. So you might at this point say, well, the reaction stopped. We're not using up any more reactant and we're not making any more product. But it's a bit more complicated than that. So let us look at the details and then we'll go to the video. So as I was saying, as the concentration of the products increases, the rate of the backward reaction gradually increases because we're getting a larger concentration of products. So rate of reaction depends on increasing concentration. And the rate of the forward reaction is decreasing because the concentration of reactants is decreasing. So we've got another graph here, which now is rate against time. So the previous one was concentration, this is rate. And what we find for an equilibrium system is the rate of the forward reaction decreases, as I've said here. It decreases, and this is the rate decreasing here. And the rate of the backward reaction increases until they become equal. And at this point, where the rate of the forward reaction equals the rate of the backward reaction, we have equilibrium. So from this point on, equilibrium has been established where we've got this horizontal line. So this is really, really important point. Now, let's have a look at the reaching equilibrium video, another little one. Now that is one of my favourite equilibrium videos. It really explains the whole situation excessively well. So feel free to watch that again if you like. You can do that by going to the electronic version of the notes on the portal. So what we find when we're looking at reactions and we're trying to work out how well the reaction has occurred, how complete it is that we often seem to get a poor yield. So for instance, when we were making our biodiesel back in first term, if we'd been able to measure how much biodiesel we had made and compare it to the perfect situation where 100% of the reactants had reacted to make the biodiesel, we would have found that we did not have 100% yield, so perfect production of biodiesel. We would have had a much lower percentage made. And so what we find is that this happens in many cases, and most of the time it's due to equilibrium. So something I want you to remember is if you are trying to explain why in a reaction you've got less than 100% yield, so in other words, you haven't got the full quota of what you expected to get as products, then there's every chance that the system has reached equilibrium. So that's an important one to note down. Okay, so we are going to finish with a video. Now, I will play this video through as part of our lesson video. After this video, we're up to dynamic equilibrium and we'll start that next lesson. So this next video goes for 25 minutes. And actually, no, I won't put it onto this video. We'll make it a separate one simply because I don't want this little video to be too hard to save. So let's stop there. On Wednesday, I don't think I'll be back at school, but either I'll do a face-to-face via Teams lesson, or maybe there'll be a video, but it'll be one or the other. I want us to keep moving through equilibrium, so it's very important that you keep up with this work. Okay, everyone, so the next video you're going to watch is the Chem Study equilibrium video, and I'll put in instructions on the portal.